one thing I want to say about that quiz, those quiz scores were low across the class. Um, these are the kind of questions I think that in a class like this with like tons of equations, tons of topics, like this is the kind of thing that you really like almost the number one job in a class like this is trying to organize these kind of questions in your head. Because if you don't know when stuff applies, if you don't know what kind of simplifications happen, um, then you can't use any of these equations effectively in real problems. Maybe in a class, maybe you could get by because you're like, oh, we just studied this, I'll do this. But like to actually use it as an engineer, this is the kind of stuff that needs to be sort of stuck in your head. It's kind of the number one objective of coming out of this class. Um, all right, so number 4. Um, we have air. I assume we're going to treat this as an ideal gas. Uh, it enters a well insulated horizontal pipe, and the pipe has a given diameter, and it gives enough properties at the exit to, um, well, it gives us a pressure and a temperature. We're thinking of this as an ideal gas, so this will let us calculate the specific volume. Bless you. Okay, so let's think, we'll break this up into state 1 and state 2. Um, or really, let's call it inlet and exit. Um, at the inlet, we have that the temperature is 330 Kelvin, and the pressure is 600 times 10 to the third pascals. Um, and at the exit, we have a temperature of 300 K and a pressure of 120 times 10 to the third pascals. Um, it says use an ideal gas model. Um, so we want to figure out the inlet and exit velocities. It's steady state. So, okay. We're given, so at the exit, um, we know that the mass flow rate, and since it's steady state, this is the same as the mass flow rate at the inlet, is equal to the area times the speed divided by the specific volume. The area is pi times the radius squared, and the radius is 0.6 centimeters. So that is 0.006 meters. So that's 1.131 times 10 to the minus fourth meters squared. Um, and the specific volume we can use the ideal gas law. So 120 times 10 to the third times the specific volume at the exit is equal to, for air, 287 times the temperature of 300. And so V exit is 0.718. Um, okay. So m dot is equal to 1.131 times 10 to the minus 4 times the speed at the exit divided by 0.718. And then at the inlet, we have the same area times the speed at the inlet divided by the specific volume at the inlet. For that, we have 600 times 10 to the third times V inlet is equal to 287 times 330. So 0.158. So m dot is equal to 1.131 times 10 to the minus 4 speed at the inlet divided by 0.158. So up here we get 0.000158 VE. And down here we get 0.000716 VI. Those two have to be equal to each other. So we can say, so VE is equal to, set these two mass flow rates equal to each other. And you get that V exit is equal to 4.53 V inlet. Okay, so we're trying to find inlet and exit velocities. Mass flow rate, and the rate of entropy production. Well, we know that So it's well insulated. So we know that there's no heat transfer. So we can use that stuff in the control volume second law and in the control volume first law. So let's just set those up and see if anything comes out of it. Um, so second law for control volumes. Um, so the change in entropy, no, we want the control volume equation. So ds dt is equal to the sum of all the rates of heat transfer divided by the temperature around the boundary plus m dot times, I can lump these together, s at the inlet minus s at the exit, plus sigma dot. And since it's steady state, we know this goes away. We've already used steady state to replace the mi dot and the me dot with just m dot. Since it's well insulated, we know that there's no heat transfer. And so we can write this as, we can write it as m dot times, I'll switch the order of those two. So S exit minus S inlet is equal to sigma dot. There is no heat transfer. Well, so we're back to being sort of stuck on figuring out that m dot. If we can figure out m dot, then immediately from this we can come up with sigma dot. So let's see what the first law for control volumes gives us. So that says the EDT is equal to Q dot minus W dot plus M dot times H plus VI squared over 2 plus GZI minus M dot times the quantity H exit plus V exit squared over 2 plus GZ exit. This is a horizontal pipe, so we're not going to worry about those. Those are the same. There's no heat transfer. This is just a pipe. There's no reason to believe that there's any kind of, it's a rigid thing. So there's no work of expansion. There's no mention of any rotating shafts or electrical power. So that's 0. Steady state means this is 0. And so what we have, if we divide this equation by m dot, is we have hi plus vi squared over 2 is equal to he plus ve squared over 2. Um, this is, so this is an ideal gas. We have already the specific volumes and the pressures and the temperatures at the inlet and exit. So HI is equal to UI plus PIVI. Um,
Can we look up enthalpy on the table with the pressure?
yeah, if yes, you could. We do have air in the website for the website. Yeah. I was so whenever you're given ideal gas, I think it's just good practice for thinking through this stuff to just try to do the calculations without the tables. Sometimes you need it. In this case, I think we'll be able to do it without the tables. Um, there's nothing wrong with that though. But on tests and stuff, there'll be times where I make you do these calculations, so it's good practice, I guess. Um, okay, so this is UI plus. At the inlet, our pressure is 600 times 10 to the third. And our specific volume, we just calculated 0.158. That was at the inlet, right? Um, so that is UI plus 94,800. And then at the exit, this is UE plus pressure at the exit, 120 times 10 to the third. Times the specific volume at the exit, 0.718. So that is UE plus 86,160. All right, so now we're going to go, so now I'm going to use these equations, sort of combine them, and we get that UI plus 94,800 is equal to UE plus 86,160. What am I? Oh, no, because the whole reason we're doing this is to try to calculate those velocities. So here's our HI, and then we're going to add to that VI squared over 2. And then over here we have UE plus 86,160 plus VE squared over 2. Okay, and now if you think of, so you can do this as UI minus UE is equal to, now we're going to use the specific heat for an ideal gas. So this is equal to CV for air times the temperature at the inlet minus the temperature at the exit.
So 30 Kelvin.
Is that what it is? Yes, exactly. So, and the inlet was higher. The exit was higher. So, just the way I have it, this is going to be negative. This is 1.0.
The exit was 300 Kelvin and the inlet was 330 Kelvin. So
Oh,
the exit, wouldn't the inlet be higher?
yep, you're right. So yes, so this is positive. So we have this times 30. So that's 30,150. And so now we can go 30,150 plus 94,800 plus VI squared over 2 is equal to 86,160 plus VE squared over 2. Um, okay, so with a little simplifying and stuff, we get 77,580 plus VI squared is equal to VE squared. And from before, we have this relationship. So right now, that's one equation with two variables. But if we now use this second equation, VE is 4.53 VI. So we have 4.53 VI all squared is equal to VI squared plus 77,580. So that says 77,580 is equal to 19.52 VI squared. And so VI is 63.03. And then V exit is 4.53 times this. So 285.51. And then we're trying to find the mass flow rate. Now we can calculate that because we have the speeds. So the mass flow rate so the mass flow rate is .000716 times 63.03.
Professor, could you scroll up a little bit?
Yeah, let me just write this down. 0.045 kilograms per second. And then we finally have this equation here. So we can calculate, so sigma dot is equal to m dot times the quantity S exit minus S inlet. And we can write this as so S exit minus S inlet is equal to CV times the natural log of T exit minus T inlet. And then minus R times the natural log of P exit minus P inlet. CV. CV. Do I have this equation sitting around? This is actually CP.
So you're dealing with no volume instead with a constant volume, right?
This is the equation that says delta little s is equal to, this comes from the TDS equations for an ideal gas. So delta S is equal to Cp natural log of T2 over T1 minus R natural log of P2 over P1. Cp is 1005 minus 287, so that's 718 times the natural log of 300 over 330 minus 287 times the natural log of why is it doing that? 120 over 600 and so we get 393.48. This is joules per kilogram Kelvin. And so the mass flow rate, no, that's not what we want. We want the rate of entropy production is equal to 0.045 times 393.48 and that is 17.71. Um, which is in joules uh, per, well, with the seconds, this is going to be watts per Kelvin. And if that came out negative, something would have been wrong. That entropy production can never be negative, but this one makes sense. Um, so, I mean, I looked at this problem and, you know, I did not see, sometimes you see a problem a lot of times and you're just like, here's the path I'm going to follow. I'm going to do this to get this to get this. I didn't see anything like that when I looked at this problem, but I just, I was like, okay, let's just start figuring out the stuff we can. Um, Came up with some expressions to saw how close we were to certain things. It gives you a hint about what kind of stuff you still need to find, and then that can kind of lead you to new equations until you kind of get it in the end.
And just one question for clarification. You can still use CP even if the pressure is changing in the example because it was always assumed that was meant.
Yes, CP for an ideal gas only depends on temperature.
So
And as long as that temperature range is reasonably small, you can get pretty good results. And we did one where the temperature range was 800 degrees Celsius, and we still got 10% error or something, So 30 degrees Celsius, like you can feel pretty good about that. What?
Smoke change the temperature.
Yeah. So as far as using CV and CP, it's all about temperature. You don't care about any of the other things. It only varies with temperature for an ideal gas. Yeah. Any other questions? Okay. Um, well, I mean, I was going to do another example problem that's sort of that same kind of thing. Uh, how long would that take? I think we have time to do this. Can't hurt to do one more example. And then next class, we're going to start just another outline. We're done with second law of thermodynamics. So we're going to go back through, just talk about where we are, try to keep solidifying all these concepts in your head. Okay, so this example. Um, so we have water. Um, Moving through a device uh, that exchanges um, enthalpy change for fluid speed change.
How would that work?
Uh, that's basically what a nozzle and a diffuser both do. Um, so I mean, you can think of the enthalpy as largely it's like exchanging pressure for speed. On one side there's a high pressure and a low speed, and on the other side there's a low pressure and a high speed. But the thing we're going to do here is we don't know which way it's going. So at one end, it's steam at a pressure of 60 bar, a temperature of 400 degrees Celsius, and a speed of 30 meters per second. At the other end, It's a saturated steam, saturated vapor with a pressure of 30 bar. Um, and our question is this a nozzle or a diffuser? Okay, so we've done, this is getting at the thing that's, um, remember the second law gives us a way to determine what direction is possible for a process. And so that's what we're trying to do here. We've done that we did that with a chunk of metal that we threw in like a, into cold water. And then we figured out that it was the only possible way that this process could happen is if they start at different temperatures and end at the same temperature. Remember doing that? Um, so we're going to do the same thing here. And the way we're going to do it is we're going to calculate the entropy produced. And the direction that's possible is the one with positive entropy produced. Excuse me. So the direction that occurs is the one
So we're going to use like ideal gas to determine the exit pressure or exit temperature due to the saturation and having that pressure.
Yeah, so we're just going to start with the second law for control volumes. We're going to try to fill stuff in little by little, and once it's all filled in, we're going to calculate the rate of entropy production. And with the inlet, you know, calling one of these two states the inlet and the other one the exit, it's that rate of entropy production will either come out positive or negative. If it comes out positive, then that's the direction that it goes. If it comes out negative, then that's the wrong direction. Um, so the direction that occurs is the one with positive rate of entropy production. Okay, so let's try it as a nozzle. Either way, we're not going to have to try the other one. If this one doesn't work, then we know it's the other one. Um, so at the inlet, we have steam. That inlet pressure is 60 bar. The inlet temperature is 400 degrees Celsius. And the inlet speed is 30 meters per second. At the exit, we have a saturated steam. And the exit pressure is 30 bar. Um, well, we don't know the speed at the exit. So what are some things that you could think of to calculate the speed at the exit? There's really only two equations, I think, that where we could hope to do that. We know that this thing is in steady state.
So the total mass, just relating them by mass flow.
Yeah, right. So those mass flows are the same, but we're not told anything about the areas of the, apertures.
The
So,
volume cancel each other out though, right?
well, we're not told that. If we were told that they had the same area, so we don't have that. So let's try the first law. Okay. So the first law for control volumes says dE dt is equal to Q dot minus W dot plus M dot times the quantity HI plus VI squared over 2 plus GZI minus M dot times the quantity HE plus VE squared over 2 plus GZE. And we have no reason to think that the height is changing. Um, this is steady state. And I forgot to write down a bunch of stuff that's important. So we do know it's steady state. No heat transfer. There's no work. And no height change. So sorry about that. That was in the problem. I just didn't write that down. Um, so that's going to let us cancel a bunch of this stuff. Steady state means this goes away, no heat transfer, no work, and then those two cancel with each other. And the MI and ME dots are the same. And so we can just write this as HI plus VI squared over 2 is equal to HE plus VE squared over 2. And for water, we can look this stuff up. I That's a good question you asked about ideal gas. It is a vapor the whole time, it looks like. So you could probably do this and get okay results for an ideal gas, but I did just use the table or the website for this. So we have um,
Yeah, because we were given the fact that it was at saturation, which means we only need one property to determine the rest of the
right,
properties.
right, that's right. So we have 3177.2 times 10 to the third is that specific enthalpy at the inlet, plus 30 squared over 2 is equal to 2804.2 times 10 to the third, plus speed at the exit squared over 2. And you get that VE is 864.2 meters per second. Really fast. And now we can go to the second law for control volumes. So ds dt is the sum of all the Q dots over T around the boundary plus m dot times Si minus m dot times Se plus sigma dot for the control volume. Steady state says this one goes away. No heat transfer says this one goes away. So we can write this equation now as, I'll divide everything by m dot, and I got Se minus Si is equal to sigma dot for the control volume divided by m dot. And you can look up these specific entropies on the website. And you get that 6.838 times 10 to the third minus 6.187 times 10 to the third is equal to this thing. And you can see that that's positive. So this is a nozzle. It's impossible for this to go the other direction.
We got to the velocity and saw that it was like over 800 meters per second that it increased. Could that be enough to say that it was a nozzle, or we have to go through the second law to confirm that?
Well, the reason that the speed was higher was, and we didn't even need to calculate that speed, did we? It didn't ask for that, but we did it. So we started by saying, let's assume it's a nozzle. And so at that point, we knew the speed was going to be higher at what we were calling the exit, But what we really needed to check was, is it possible? Or is it only possible going the other direction?
All right, yeah. Second law was needed to make sure it actually was possible.
Right, yep. And so if you switched all this, if you assumed that it was a diffuser, you would get the exact opposite sigma dot over m dot, and it would be negative, and it's not possible. Any other questions? Okay, so we'll start doing another little summary next time. Maybe we'll finish it in one class. And then we'll get into the last topic of the class, which is sort of a real power plant operation.